All right, good morning, guys. I'm going to have you watch this video. The PowerPoint's also there for it if you want to go back, or you can hit pause on this. A lot of these slides are already been produced, but I'm going to work out a few like I normally would on the board on the PowerPoint. So patience with me because I'm not the best at writing on my iPad. So we'll see how that works. Reminder, hopefully you have a much better handle of the optimization. I hope your WebAssign's done, but I'm not grading it tomorrow because I'm not here, or Friday because I'm not here. So you have through the weekend, I guess, to get it done. But I will be grading that, and you will be quizzed over the optimization, just optimization, on Tuesday. But here's your notes for section 3.7 differentials. All right, so there's our objectives, and we're going to go through the tangent line, a differential, talk about propagated error, and using a differential to approximate. Tangent line approximations. So Newton's method, if we remember that, Newton's method was a guess, and then we got closer and closer by using the tangent line to approximate a zero. So we're still using that concept where we see the y minus f of c equals f, the derivative. There's your tangent line of the x minus c. So you know this. You guys have been working with this. Because c is a constant, y is a linear function of x. Moreover, by restricting the values of x, to put it in this, we can always approximate using tangent lines. And that's what we're talking about here at the tangent line approximation. So I have an example here. Using a tangent line approximation of the function 1 plus sine of x at the point 0, 1, then use a table to compare the y values of the linear function with those of an open interval containing x equals 0. So we plug in 0 and we know 0, 1. That's where that's coming from. So here's our step. We first get the derivative. The derivative of 1 plus sine of x is the cosine of x. So now I use this point and this derivative to get, I plug in, remember it's y minus 1, so f of 0 is 1, plus the derivative x minus 0. So you're used to seeing y minus y equals derivative x minus x. There it is, just solve for y. So we plug in, and I get it down to 1 plus x. Y equals 1 plus x. That's your tangent line approximation. Then we take that values and we use a table. So here's my x values. Here's the original function. Here's the derivative. And notice how, as my x gets closer to 0, the more accurate my tangent line is to the actual y value. And that's what it's called by linearization. Okay, so I can conclude this by, here's our tangent line, here's the graph. The closer our tangent line gets to 0, the more accurate it becomes. So I have one here. Now this is pretend where I go to the board, and let's try this one. So I give you the function x plus 3, or the square root of x plus 3 here. I'm trying to get this to work here, so patience with me. So let's see here. Let's see if this, there we go. Let's change the ink color though. Okay. So first thing we want to do is we want to take the derivative of f of x. So we know that would become f prime of x. See, I told you to be patient because my writing's not the best. That would be what? 1/2. Now it would be x plus 3 raised to the negative 1/2. And then the derivative of x plus 3 would be 1. So there's our f prime of x. So if I wanted to know the slope at that point, we're going to find f prime, and we're saying linearization at a equals 1. So f prime of 1, so I plug in 1, and I get 1 over 2 times the square root, because I put the radical since it's raised to negative 1/2 in the denominator. 1 plus 3 is 4. The square root of 4 is 2. 2 times 2 is 1/4. So there's our slope, 1/4. Okay? The next thing I'd like you to do is, if I have the value 1, what's the output? I plug that back into the original function. So the square root of x plus 3, the square root of 1 plus 3 is 4, square root of 4 is 2. So our point is 1, 2. So let's write our tangent line. You guys know how to do this. You're going to say y minus 2 equals slope 1/4 times x minus the x value, which is 1. And now I'm going to solve for y, and that becomes y equals 1/4 x. I distribute the negative 1/4 through and add 2, that becomes positive 7/4. Okay, so I have that value. I have that tangent line. So now let's compare it. Let's use an example here of the square root of, let's do 3.98. We're going to use linearization, so the square root of 3.98. I made that up. So it'll go, where's that come from? I made that up. How is that equal to the square root of what was our original function? X plus 3. Now let's solve for x. We'd square both sides. So now I have 3.98 equals x plus 3. I'm going to subtract 3. X equals 0.98. Okay? So now you go to your tangent line. Y equals 1/4 x plus 7/4, and you plug in this 0.98 for x. That's what you saw in that table. So 1/4, what's x? 0.98 plus 7/4, and I plug that into my calculator. That gives me 1.995. Now, that's the linearization answer. If I would have just gone to my calculator and typed in the square root of 3.98, because remember, this is a process before calculators, I would have gotten 1.99499 and so forth. I think that's a pretty good approximation. Okay? So hopefully, seeing me walk that through, I found the slope, the tangent line, I broke it down and found what x is, and I went from there. All right, I'm going to continue on here. So differentials. When the tangent line of the graph of f at the point c comma f of c, we understand that delta x is the change in x, delta y is the change in y. We can use this. Again, there's that tangent line is using an approximation of f. Now, when delta x is small, that's the change in x. When delta x is small, the change in y will be denoted by delta y. And this can be approximated as shown. Delta y is equal to f of c plus delta x minus f of c, which you can see here from the diagram I put together, which is approximately equal to, guys, look, the derivative of c times delta x. For such an approximation, the quantity delta x is traditionally denoted by d of x and is called the differential. The expression f prime of x d of x is denoted by d of y, and this is known as the differential of y. So d of x, differential of x, f prime of x d of x is denoted by d of y, which is the differential of y. So here's our definition of differentials. I don't need to repeat it again. I'll let you write it down. Note this, delta y is approximately d of y, or delta y is approximately f prime of x d of x, and we're going to revisit this. So I have an example here. Let y equals x squared, find d of y when x is 1, d of x is 0.01. Compare this value with delta y for x equals 1 and delta x equals 0.01. So I'm going to have this go through here. So we find d of y. We take the derivative, d of x. So we find the derivative of y, which we all know is 2x. We plug that in times 0.01, because I told you we're going to, delta x is approximately, or is 0.01 right there. And again, we get the 2 because we take 2 times the derivative of x squared is 2x. So we plug that in, and we get the value 0.02. Now using delta x, 0.01, the change in y, so this is the change in y. is f of 1.01 minus f of 1. We go through the process here, and look how similar they are. So you can see by this diagram, the change in y, d of y, is approximated by the differential of y, d of y. Again, I have a table showing the difference in the two of the delta d of y versus the delta y. All right, error propagation. I'm going to go through this. I'm going to, at the end of this video, I'm going to pretend we go to the board again. I'm going to work out one of those differentials. So we know error propagation. I bet if you take in chemistry, AP Chem, they probably talked about the error propagation. Physicists and engineers tend to make liberal use of the approximation delta y by d of y. And we go through the process here again, what we call the propagated error. Here's an example. The measured radius of ball bearing is 0.7 inches. The measurement is correct to within 0.01, a hundredth of an inch. Estimated the propagated error in the volume. So here's the volume. We tell you the radius is 0.07. We tell you that the propagated error is within 100, so it's between negative 0.01 and 0.01. And we know delta V is approximately equal to d of V in respect to r. So we're going to take this derivative, just like related rates, take the derivative. So we know the derivative of 4 pi r squared d of r. We plug in the 0.07, and there's our propagated error. All right, calculating differentials. This is pretty straightforward. I have this here for you. Let me just take you to the table. So example, if I give you the function x squared, the derivative of x squared is the derivative of y in respect to x is 2x, and then you just simply solve for d of y. So it would be 2x d of x. So all you do is take the derivative, d of y d of x equals the derivative, and then you just solve for the d of y, and there it becomes your differential. So I have some examples here. So the derivative of 2 sine of x is 2 cosine of x, and then d of y would equal 2 cosine of x d of x. All right, so calculating differentials, I have an example for you. Approximate 1 point, or the square root of 1.1. So we could go to our calculator right now and just find that value. And I think that answer, the square root of 1.1 is 1.0488. So if I plug that in my calculator, I know it's 1.0488. But we're going to use a differential to show you how we could approximate that answer. So I want you to make sure we write this down again. We know f of x plus, you can tell I'm not very good at writing this, delta x. So that says f of x plus delta x is approximately equal to f prime of x d of x plus f of x. Okay, so we're going to use that. We're going to work with it. So when I see the square root of 1.1, I got to think of this as, well, let's treat that 1.1 as x plus delta x. So we know x plus delta x equals 1.1. And if I made x 1 and I made delta x 0.1, okay, so let's write that down. That equals 1.1. So we're going to say x is 1, delta x is equal to 0.1 or 1/10. Okay, I guess I didn't need to write this. We can see that 1 plus 0.1 equals 1.1. So let's think of, I want to make sure I tell you guys this right. Let's think of f of x as equal to the square root of x. Okay, so then let's find the derivative. F prime of x would be equal to 1 over 2 square root of x. I don't think I need to go over that. I think you guys should have that down. So I can approximate the square root of 1.1 using the differential formula. It's approximately equal to f prime of x. So we know what f prime of x is. We just found it. It's 1 over 2 square root of x times d of x, which we say is approximately delta x. And what did we say delta x was? 0.1. Now I'm going to write it as 1/10. It's a 0.1 1/10 plus f of x, which we said was square root of x. Now, what's x? I come right back over here. I told you guys that x was 1. So I'm going to plug in 1 for x. Now, I'll be careful again. This is d of x, which is approximately delta x. So that's where the 0.1 1/10 comes from. So I'm going to go in here, and I'm going to plug in 1. So for x, what square root of 1 is 1. 1 times 2 is 2. So I have 1/2 times 1/10 plus, I'll write the square root of 1, which is 1. So now this is approximately equal to 1/2 times 1/10 is 1/20th, plus square root of 1 is 1. 1/20th plus 1 is 21/20ths. And if you take your calculator and you type that in, that's 1.05. That's a pretty good approximation when we compare it to what we said it was exactly, 1.0488. And I know that's an irrational number, so it keeps on going. So there's an example how we use a differential to approximate. Okay, I don't need that other slide. I was worried I might need the other slide. So your homework is 3.7 web assignment. Guys, I know this was fast. I know some of it was confusing. Look through it, work through this assignment. I'm banking on this becoming more clear as you work through problems. And remember, next class you have an optimization quiz.